different ways we have to use, and these are indirect methods. You know, like imagine that you're standing there and then a train goes past or a car goes past. What happens to the sound? You know, right? You hear the pitch. First it's higher and then it's lower. Why does that happen? That happens because the sound waves, the sound of the truck or the car or the train, is compressed as it's reaching you before it passes you, and so that's makes the pitch higher, and then it's extended out after the train goes past, and that stretches it out, and so it makes the pitch lower. It turns out the same thing happens for light. And for light, instead of changing the sound, it's light. So it changes whether the color of the light. If a star is moving toward us, it shifts the light to be a little more blue. And if it's moving away, it shifts it to be a little more red. And it turns out that a planet circling a star alters the star's orbit. So not only is Jupiter orbiting the sun's orbiting Jupiter. The sun is going in a little dance, and that little circle is very small, but that causes the sun to move back and forth, and other stars that have planets are doing that same thing. And so we can detect the change in their color. Oh, look at that star. We can observe it and see, oh, now it's a little more blue, now it's a little more red, now it's a little more blue, in a clockwork pattern that shows us that that star is going in a little circle. And that tells us that there's a planet going around the star that's tugging the star in a circle. And so we can discover that planet even though we haven't actually detected any light from the planet. But what's cool is the more massive the planet is, the more it affects the star, and the bigger that signal is, the more blue and the more red it will be. So that method tells us how massive the planet is, and it also tells us the length of the planet's year. In other words, how long it takes this planet to go around the star in its orbit. And that's already a fair amount of information. We don't know how big the planet is, we don't know how bright it is, but there are other methods we can use for that. For example, imagine a star, and even if we can't see it, it's actually a disk in the sky. If you imagine looking at the sun through a solar telescope, and imagine a planet passing in front of that stellar disk, that star as viewed from the Earth. It would block out a part of the light. For instance, if you Google Venus transit of the sun, you'll see pictures of the sun's disk and a little black dot sitting in front of it. It's basically Venus hanging there between the Earth and the sun. It's blocking out part of the sun's light. And we can't take an image like that of another star, but if a planet is doing that, it blocks out part of the light, and so the total amount of light from the star will drop. And if the planet's area is 1% that of the star, then the star's light will drop by 1%. That's easy to detect. And so we can detect that from ground-based telescopes, and we can detect it from spacecraft, like NASA's Kepler spacecraft mission, for example. And usually we know how big stars are, and so the size of that signal tells us how big the planet is. Like Jupiter is a tenth the size of the sun. That means the area is, think about the area goes as the size squared, so the area is 1%. And so a Jupiter-like planet crossing in front of a sun-like star that way would block 1% of the star's light. So, and if you think about it, if we have both the size of the planet from that second method, that's called the transit method, and if we also have the mass of the planet from that color shifting method I said at the beginning, if you have the size and the mass of the planet, that means we know how dense or fluffy the planet is. We know the density of the planet. We can say something, is this a gas planet that's just hydrogen, super lightweight? Or is this a rocky planet, maybe even dominated by rock and metals, or something in between? So we're starting to get more information. Now let me say something about the type of planets then that we're discovering. We have in our solar system 8 planets. There are the rocky planets, Jupiter, Saturn, the gaseous planets, Jupiter, Saturn, Uranus, and Neptune on the outer, very far away from the sun. We have the rocky planets, Mercury, Venus, Earth, and Mars, and they're kind of spaced pretty regularly. It turns out that many other star systems aren't like that. There are cases where Jupiter-like planets are right next to their star, 20 times closer to their star than Earth is to the sun. They're being blasted by starlight. They're so close to their star that the year of these planets, the time it takes the planet to go around the sun in its orbit, is only a few days long. And they're getting so much starlight that their temperatures are heated to 1,000 or 2,000 degrees. And rocks at those temperatures melt and even vaporize. And so you can imagine gases in the atmosphere, that's gases, that's vaporized rocks, and then the rain forms, and the rain is actually the rocks crystallizing and falling. So the climate and weather on these planets is very, very exotic. They may have winds, speeds that reach several miles per second, way faster than on the Earth. And so we can actually characterize those planets now. We can learn about their structure and about their temperature. Other planets are in between the rocky and the gassy planets. One interesting thing is in our solar system is the planets fall so cleanly in rocky versus gassy. You don't have anything in between. Well, what would be a planet like if it were in between the Earth and Neptune? What if a planet was double the size of the Earth, 4 or 5 or 6 times more massive? We don't have any planets like that in our solar system. Are those rocky bodies with a thick atmosphere? Are they gas giants? So we can now characterize that, because it turns out that type of planet is the most common planet in the galaxy, as far as we know, according to the data that I've described.